Okay, we are all ready to start.
Okay. Yeah, okay. So Horacio, yeah.
Yeah, then I start.
Yeah.
Okay. Oh. So you can see that.
Okay. Yeah.
Okay, I start then. Well, hello everybody, and greeting from Bariloche. Thank you for coming. I will talk about entanglement in quantum field theory, or maybe that more generally things that we can do with quantum information in quantum field theory. I planned a review of old and new results in this subject, and today I will talk about mainly general things and introduce some tools. The next lecture will be about irreversibility theorems. The other about entropy and energy bounds, and the last one about entanglement and symmetries. Please ask as many questions as you want. Maybe you can stop me at some moment if I'm distracted and not looking at the questions or whatever. I also uploaded at the web page and notes that are more complete than what I want to say, what I can say in the lectures. So if you want to ask questions about these notes, you can also leave the questions in the web page, and I will be looking at that this week and answering questions.
Okay.
Well, I will start. My first transparency is about is kind of a philosophical remark, or maybe the way I like to see this subject. We have quantum field theory that have several formulations. The most natural one is in terms of quantum fields, and is known from many years ago, from the 50s, that you can as well describe the theory in terms of correlation functions that are numbers attached to this to the polynomials of the fields. So all the information of the theory is already in the vacuum correlation functions, the expectation values of these operators, to reconstruct the full theory out of these expectation values. Now that there is also another formulation that he had Kastler in '64, that is this algebraic formulation, that where the main objects are not the quantum fields, but the algebras of operators in certain regions. This diamond here, I will explain what this diamond is, but these diamonds in space-time, a region of space-time where you attach an algebra of operators that are formed by the quantum fields there. And somehow it's a minimalistic way of describing the quantum field theory. You put the less axioms as possible, and it's a kind of basis-independent formulation of the theory, because it was thought in this way because you can generate the algebras with different fields. You can take a scalar or a scalar to the power cube, let's say, and they generate the same algebra. So it doesn't depend on what are your preferred fields to generate the algebras. And also you can have dualities given the theory in terms of different kind of fields, by giving the same theory with the same algebra. But even if this formulation is very old, this step of giving numbers to the algebras was not really done in the past, and is very recent. And if you think what number you can produce for an algebra out of the vacuum, let's say, immediately you recognize that there is only this information quantities like the entropy or mutual information, ranging entropies that you can play with there. So one natural question would be in this approach to see if you can formulate, for example, the theory only in terms of entanglement entropies and in a universal way to describe the theories in this way. So let me pass to some definitions. Well, an algebra is what you expect it to be. It's a set of operators in Hilbert space. You always put the unit there. You have the numbers inside the algebra. Given two operators, you have the products and the linear combinations, and the adjoints are also belonging to the algebra. It is important that this other algebra you can form, given an algebra A, you can form this other algebra that is the commutant algebra, that is just a set of operators that commute with A. And in fact, the von Neumann algebra, or an algebra of operators in Hilbert space, can be defined as as a set of operators that coincides with the commutant, say the commutant of the commutant. Well, this is what is an algebra. What is a state? A state is just a function that gives you the expectation values, let's say, of the operator. Is linear, is positive in the sense that it gives you a positive number for any positive operator, and for one you give you one is normalized. So this is a general way to describe a state. And once you have an algebra, let's say a finite dimensional algebra or some type of algebras, you see that a state defined in this abstract way always produces an element in the algebra. So it's an element of the algebra now that is a density matrix that is devised such as to reproduce the expectation values in this way. It's a trace of the density matrix times the operator give you the expectation value. So a state produces an operator itself inside the algebra in this way. That is the density matrix. And with this density matrix, we can start computing entropic quantities, and this is the most important one. Is a von Neumann entropy. Is just a generalization of thermodynamical entropy for any density matrix that is not thermal. For a pure state in the global Hilbert space, you always have this property that the entropy of an algebra is equal to the entropy of the commutant of the algebra. This is what is usually said in the way that the entropy of a region is equal to the entropy of the outside of the region for a pure state. But it is more precisely given by this way with a commutant, and this will be important in the last lecture. And when you have a global pure state in this way, this quantity, this number, this entropy, is a measure of entanglement between A and A prime. It's a precise measure that you can, it has operational interpretation in terms of the number of EPR pairs or entangled qubits that you can extract from here doing just local operations in A and A prime.
There is some question in the chat. You want me to read it?
Yes, please.
Okay, one is, how does this definition of state connect with the idea of lying in a Hilbert space?
Sorry, connect with what?
The idea of lying in a Hilbert space.
Yeah, well, this is more general somehow. You can produce states, of course, by states, by vector states in the Hilbert space or by density matrix in the Hilbert space. But more generally, you can ask only these properties. Normal expectation vacuum expectation values will satisfy this.
Mm-hmm. And then another question is, sorry, what do you mean by trace?
Well, I prefer if you are interested in this point, because it's you can look at it in my lecture, in my notes. The trace, you can define it intrinsically in the algebra. You can define it intrinsically in the algebra. If it is a finite dimensional algebra, you can do that. We will soon see that in the quantum field theory, for this type of algebras, you don't have this trace, and you don't have even the density matrix you don't have. So, but still, we can think in the density matrix and the trace in terms of a cutoff theory, and we can take the limit, and we will have this mindset in these lectures. You can do most of the important things in a more abstract way, even for algebra of quantum field theory, but I prefer to go this way, that is easier.
Okay. So on a third question, says from Monire Ahmadpur, now for pure state, we don't have entanglement?
No, for pure state, you can have entanglement, or you can, if the entropy on your algebra, let's say the algebra is attached to this region, let's say, so you have a global pure state, and you compute the entropy. This entropy will measure the entanglement. Yeah. Mm-hmm. If the entropy is 0, then there is no entanglement. The state is a product between inside and outside. This never happens in quantum field theory. There is always some entanglement. In fact, the divergent amount of entanglement. So, but I will stress that I'm not that interested in the operational or quantum information meaning of entanglement, because I'm more interested in the fact that this is an entropy. So, as we will see, all entropies can be seen as entanglement entropy in a bigger Hilbert space. So there is no really intrinsic meaning of, for a given algebra, that this entropy is entanglement. It can always be thought as entanglement with something else, with some, let's say, thermal mass or whatever. So if you have a, sorry, then let us think in quantum field theory. In quantum field theory, you want to produce, for example, this region B, you want to produce an algebra for this region B, then you can take smear fields inside this region and start multiplying them and producing an algebra. But you will see that the algebra for B will be the same as the algebra for this diamond here. Why is that? Because this operator here in Heisenberg representation will satisfy some equation of motion that will relate this operator to some operators at t equals 0, let's say, or around t equals 0. So in fact, the algebra of V is the same as the algebra of this diamond. So we can think the algebras are attached to these diamonds that are domains of dependence of pieces of spatial surfaces. Other way to define this diamond is to say that we start with B, we take the spatial complement of V that we call V prime, the spatial complement that is all points that are spatially separated. And then we take it again, the spatial complement of the spatial complement, and then you get this diamond. So it's very similar to this idea of taking the commutant of the commutant. And of course, these things are related in the sense that given an algebra, the algebra of the complement of the causal complement, that is the part that is outside, spatially separated, will be included in the commutant of the algebra. Because of course, all operators spatially separated commute to each other, because otherwise there is no causality. So otherwise you could send signals faster than light speed from here to there. So in this formulation, The important things that you want to look at are the algebra attached to causal regions like this one, this diamond. And you can say, well, where is the information of the theory in this representation? It would be in the algebras itself. But it turns out that it's not in the algebras, because all the algebras for all quantum field theories in all dimensions are the same mathematical objects, are some type of von Neumann algebras, a special type of von Neumann algebras that is always the same. It's like in quantum mechanics, we always say that the Hilbert space is always the same. There's no much more structure in the Hilbert space itself. Where is the information of the theory, the particular theory, is in the way the algebras are related to each other and to the vacuum. For example, this little algebra here have to be produced by, generated by this algebra of the small diamonds lying here. So this small diamond will generate a big algebra, and this then is inside these things. But the way it fits inside this product of algebras is determined by the dynamics. So, and the entropy then, following this idea, the entropy is a function of the causal regions. So it's a function attached to this causal region, to diamonds. Or what you can say is also attached to the boundary of the things, because the boundary automatically is in one-to-one correspondence to this diamond, or to a piece of a spatial surface, but you can take several spatial surfaces with the same diamond. So let me begin then trying to understand how the entropy looks like in quantum field theory, taking the simplest possible example, and we go to a lattice model in such a way we can compute things in a pedestrian way. We take, for example, in this example is 2 + 1 dimensional, and take a vacuum state in square lattice of a scalar field. You discretize a scalar field. It's a free scalar, so it's similar to phonons in a solid. And then I want to put this in a computer and compute the entropies. And it turns out that in general, it will be, for an interacting spin model, it will be very difficult, because you have, for example, spins here, and then you have a Hilbert space with dimension that grows exponentially, and the density matrix will be exponentially large for a large number of points. But as the case here is a free field, then it turns out that in the free field, it means that the correlation functions, all the correlation functions are given by the 2-point function, by the Wick theorem. So it means that there is a reduction, a simplicity of the state. It's a state that is called Gaussian. And it turns out that you can compute the entropy in a region just knowing not necessarily all the correlation function, but just the 2-point function. So it's a function of the correlation function, which is an n times n matrix, where n is the number of points. I will not review the formulas for doing this, but there are in many places in the literature. You can put the model in the lattice and then start making computations.
You can do it analytically, this calculation?
You can do analytically the expression of the entropy in terms of the correlation function here, and you can compute analytically the correlation function in the lattice for the vacuum state. The entropy will depend on the shape, and is not easily analytically computed. Let's say you can put it in a computer. Of course, in the continuous limit, you can compute several things analytically. For example, I will describe something here that you can compute. But in the lattice, it's more difficult, let's say, to get analytical results. It's more easy to get numerical results, but more difficult to get analytical results, because there is this structure, translation symmetry, rotation symmetry is broken. It's more complicated state.
There is a question in the chat.
Yeah.
It says, in the continuous scalar field satisfies Hague duality. Can we see the same for that model?
Yeah, Hague duality will mean that the commutant of this algebra is equal to the algebra of the outside part. In general, it's smaller. High duality means that these two things are equal. The commutant is equal to the outside. So somehow it's a completeness of the net of algebras. And I will talk more about this in the last lecture. That is important property. In the scalar field, effectively, you have a high duality. It was proved by Araki, and I believe it's easy to prove it in the lattice too.
Okay. And then another question: is there a similar notion of entropy based on the operator algebra in 0+1 dimensions?
0+1 dimensions.
Yeah.
In quantum mechanics.
Quantum mechanics.
Quantum mechanics. See, yes. All what I say here is just can be applied to quantum mechanics. It's just a different way to think. You can think entropy quantities or information theory quantities are things attached to an algebra and a state. But it's not that different from the usual thing. It's more general, let's say. But it applies to any quantum theory. Any quantum model has an algebra of operators and has states on these algebra operators. Mm-hmm. It's the very general setup.
Okay.
So what is the result? I take a square. Of course, I aim to the continuum limit, to the continuum theory. I'm not interested in the lattice model, but in the continuum limit. And then for that, I can increase the size of this square or put more points, what is the same for this massless case, put more points inside. And you start see, you compute the entropy and you see this law. And this is a linear law. And this is interpreted as a perimeter, let's say a perimeter or area in the 3+1 dimensional way of saying things. Is an area law. Is something that depends on the boundary. Mm-hmm. Increases with the boundary, with the size of the boundary. So you have an area law here for this 2+1 dimensional model. But you also have, this is very straight, but if you do a fit of the data, you can see there is a subleading term here that goes logarithmically. How you do that? You extract the linear term, and you see that you get this. So the full law has a perimeter. Sorry, here it has a perimeter term and has a logarithmic subleading contribution. And the model is massless, so you don't have any other parameter. So if you put the lattice spacing, it has to be perimeter over lattice spacing, and it has to be logarithmic of the size of the square divided by some cutoff distance that here is the lattice spacing. So you see that in the continuum limit, you get divergent contributions. These two are divergent contributions. And you can start doing more experiments to see how these things changes for different shades, for example. And here I take, for example, this other shape. Again, scale it in the lattice and see how the entropy grows. And it gets a perimeter. Again, it's a perimeter with the same coefficient. So we have the same coefficient before. It's an area term. And a logarithmic term that is 6 times over 4, the previous result. And this means this is interpreted that as that you have here you have 6 vertices, while previously there were only 4 vertices. And you can start doing the same type of calculations and and see that if you put more vertices, you get something that increases linearly with the vertices. And if you put vertices that are not squares, 90 degrees like this, but different angles, you see that the coefficient of the logarithmic term depend on the angle. But it's something that depends locally on the angle and on the different vertices, and a sum over all this. And then you can do another experiment. For example, here I take a square, but in a different angle with respect to the lattice. And again, I get a perimeter term, but the perimeter term now has a different coefficient. And while the logarithmic term has the same coefficient, it's the same as before. So this means that the area term does not have the rotational symmetry you expect to have in the continuum theory. So the area term depends on the way you regularize your theory, in the way you put a lattice. If you put a different lattice, you get a different area term, while the coefficient of the logarithmic term does not notice the lattice. So these terms that do not depend on the regularization are called universal. It means that they are really the ones that you are aiming at, the ones that belong to the continuum theory, while these others, like the area term, are non-universal in the sense that depend on the way you approach to the continuum theory by a cutoff theory. So we will be mainly interested in these universal terms. So with this simple information, let us try to understand what you generally expect for a general structure of the entanglement entropy for any region. The first thing, as we have seen, is that you have these divergent pieces, the logarithmic and the area, that are local on the boundary. They increase, for example, the area term increase with the boundary, and the vertices here increase additively with the vertices. And this can be easily explained by saying that the divergent pieces give contributions from entanglement for very small distances. And as you put more and more points in the lattice, you will get more and more contributions that are short distant correlations across the boundary, or short distant entanglement. So it's natural that the divergent pieces will have some power laws, and for each of these terms in the power law, there should be some coefficient that is additive on the boundary. It means that the additive independently along the boundary. This coefficient depends only on the ultraviolet physics and the cutoff in general, and the geometry, but it's independent of the state because it's very high energy, and then it depends only on the vacuum structure. And of course, the dimensions of this term and the power of the cutoff have to sum zero because the entropy does not have dimension. And then you have also a finite piece that depends on the region, that in general will contain an entropy that is non-local in nature. Non-local is entanglement, non-local across the boundary, and depends on the state in non-trivial way. So this is the one that contains most of the information. Most of the information is in the finite piece. If you have the idea that in the ultraviolet, we have a CFT plus a perturbation of the CFT. So we have a CFT plus something that is a perturbation with a relevant operator. This is the action, not the entropy. This is the action of the theory. Then you can see that you can see better what you expect here, and then you have you expect that you have powers of the cutoff, powers of the coupling constant, for example, the masses that you put in your deformation of the ultraviolet theory, and you also have something geometrical where this divergent term attach that can be integral because it has to be additive on the boundary. It has to be an integral, and it can contain also curvatures depending on the geometry of the boundary. So I have put here some example to make this more clear. That is a sphere in 4 dimensions, for example. So taking this idea, we can see the structure of the entropy. For example, if I have a CFT, I don't have any masses. So I only have to construct my entropy, the geometry, and the cutoff. So
There is
the
a
first thing,
question, Horacio. Is the statement that the coefficient of the logarithmic term does not notice the lattice is justified numerically only, or one can prove it independently?
the logarithmic term, you can see that. I will describe that here. For example, here I'm in 4 dimensions, right? I get a logarithmic term. Why I get the logarithmic term? Because I have because I can expanding my entropy. I have the possibility of putting a coefficient here that is additive on the boundary and has 0 dimensions. Why has 0 dimensions? Because it's the integral over a surface of some curvature that is just the curvature of the sphere. So this has 0 dimensions, is local and additive, and then this has 0 dimensions as typically a logarithm. And this coefficient is something that is called the Euler anomaly. I will explain it later. And then, but now this object doesn't have dimensions, but still has a logarithmic dimension. It has to be compensated by something like the logarithm with the same coefficient, like the logarithm of the radius of the sphere, because you cannot put anything else. Why I put 4a here and 2a integral curvature? Because this integral curvature can be done, and it's just 2. So this is 4a, and this is 4a. It has to have the same coefficient to kill the logarithmic dimensions. So regarding your question, you can say, well, what happens, why this coefficient is universal? Because it's a coefficient of something that is non-local in nature, and is large distance physics. Is the same coefficient. It has to be so because the logarithm connects them. So this coefficient is universal because anything you do with the cutoff, you still have this logarithm r here with the same coefficient. Now, suppose now that you have a quantum field theory in the ultraviolet. So you are taking small spheres, very small spheres. Then it's different from the CFT in the sense that you have the possibility of having mass terms or deformations of the ultraviolet theory, and then this G can enter in your expansion. You can replace powers of the cutoff here in the area term, for example, by powers of the dimensionful coupling constant, and you can have to match the dimensions. And then so your area term gets different with different powers of the cutoff, but it's still an area term. It's still is local, and it's an area term. And then you have still the same logarithmic coefficient. It cannot be changed by this G, because otherwise you have to compensate with a positive power of epsilon, and then we are not taking positive powers of epsilon. Epsilon is always the cutoff is going to 0. So it has to be the same. And then I have put here the first, let's say, non-local contribution to the entropy. That will be some power of the coupling constant and some power of the radius of the sphere. This is a non-local contribution, finite contribution. And now with the same ideas, you can also think in the infrared. So very large spheres with a scale much larger than any scales in the theory. why you can think about that in the same terms? Because now all the massive fields that are decoupled in the infrared still contribute to the entropy because the correlation functions across the boundary for regions very near the boundary, in the sense that you have a large radius and the mass scale is very small with respect to the region. So they will contribute to the entropy again in a local way, because these modes do not talk with the others. So you have a local contribution again. So what is the difference then when you write the the expansion? You can think again, you are in the infrared, so you have a conformal field theory at the infrared and some perturbation now by irrelevant operator with dimension greater than d. And then if you, how can you write the entropy? You write it, the divergent pieces has to be the same, because the divergent pieces really depends on the cutoff. So it depends on the ultraviolet. The divergent piece is exactly the same, I just copied here. But the area term gets a new contribution that is that depends on the full theory, let's say the running of the theory, and gets a contribution that is finite, that is given by this mass. It's a mass that is non-perturbative computed in the theory. And then you can also have corrections to your logarithmic term, because now you have a scale. You can have some coefficient time logarithm of some mass. So now the logarithmic dimensions of the cutoff, the logarithmic dimension of the mass have to be compensated by a logarithmic dimension of the radius of the very large sphere, but the coefficient has changed because of this. And then I put also here some non-local contribution as was this one. It has the same expression, but now delta is the dimension of a relevant operator is greater than d, so this contribution gets smaller as you make the size of the sphere larger.
There is a question.
Yeah.
Yes. Can you not have a log epsilon over g in the UV? Log epsilon over GUV.
What is GUV? Sorry.
Yeah.
Okay. Okay. No, because you are in a perturbative regime, so you only expect to have powers. You only expect to have powers of well, in some specific dimensions, maybe you can have a log G if the power is just 0, let's say.
Mm-hmm.
Yeah. But what you are thinking is so these changes of the divergent pieces are always like power loss because of it's a perturbative thing. But your log G is somehow containing this. You have this log M is of course a log G. Because if you are deforming with one parameter, let's say, all the masses of the theory will be dependent on this parameter, but it's something different in the sense that it's non-perturbative. In order to compute this, you have to understand the full theory. Mm. This is finite contribution. Okay, any other question? Oh, well. So this is what, how you, here I say, well, the most important, you have these coefficients that are universal, and these pieces are universal that are finite. But then how do you extract from this rubbish, let's say, from this rubbish that can change, you change your epsilon, it changes. you extract all the useful information. Well, there is a well-known way, a unique way to do that, that is not consider the entropy, that is somehow that is divergent in the theory, but is considering this combination of entropies. You have to do combination of entropies. In such a, for example, here I take two balls, and the combination of entropies is such that local things in the boundary appear twice here in the region A, in the region B, and with a different sign, the region A union B. So they are canceled. They are canceled. And it turns out that this particular combination of entropies is called mutual information. That is a very well-known quantity in quantum information theory, and just measures in a precise way the correlations of the theory in these two algebras. And doing this calculation in the lattice, you will see that these are circles in the square lattice. They start fluctuating as you go to larger radius, but it will turn to a constant. And in this particular example, this constant is something like 0.5. It's a very small number. It's much less than 1 bit. And you can see that what the algebras, of course, are infinity dimensional in the continuum, and you have a fraction of a bit of mutual information, of entanglement, let's say. So entanglement is very, very small in general in quantum field theory, but what is large is the number of degrees of freedom. It's very large. And in fact, if you take these two regions to, instead of being separated, you take them to approach each other, you will see that mutual information increases, and when they touch each other, it diverges. So it reproduces somehow what happens with the entropy. Well, but this is the mutual information, but how to extract, for example, I have a circle here. I want to extract the constant term, but some useful constant term. If I do the calculation in the lattice, I will see an area law. And if I want to extract the constant term, I will extract some, I will extract some constant term from this law, and it will give you these fluctuations. You will never get a constant number in the square lattice. If you do other cutoff, you get better chances. But well, the way to do that is just to take the mutual information between some circle and some other circle, the outside part and the inside part, separated by some distance now, that is a physical distance. And you take the mutual information divided by 2 and take the continuum limit. And then after taking the continuum limit, give you some precise finite number. And after taking the continuum limit, you take the epsilon small here. But this is a quantity of the continuum now. And once you take this epsilon small, you can expand in an area term and in a constant term, and then you get a precise number that you can compute by other means. Is just this number here. So this gives you a precise way to make a regularization of the entropy in the continuum model itself, if you want, just considering the mutual information. Now, of course, the lattice is not the most common way to compute things in the continuum theory. We have this replica method that I will not talk much about because you have heard last week about this. It's well known. You take the path integral in the half plane. It gives you the wave function out of the vacuum. You take 2 copies of that. You produce a density matrix. You sew them outside the region you are interested in and give you the density matrix in the region W with 2 boundaries. And then you take copies of this, in this case 3 copies, to produce the traces of powers of the density matrix. In this case, trace of rho cube. And with this, if you know how to compute the partition function, then you can compute the traces of these powers, and with these traces of these powers, you compute this quantity that is called the range entropy. It's another information quantity. It's called the range entropy, that is basically the logarithm of traces of powers of the density matrix. And in particular, in the limit n equal to 1, you get the entropy, the von Neumann entropy. It's important that when you do this construction, for example, here I take 3 manifolds, 3 copies of this manifold with a cut along the region I want to compute the entanglement entropy. And then
sorry, Horacio, there is another question. Just the question is about the epsilon to 0 limit in the mutual information. It says, does this limit always exist?
If you are thinking the cutoff here, in the cutoff, this limit always exists and give you a finite mutual information. If you here I talk about this, and then I also thought about, I have the mutual information separated by a physical distance, a small physical distance. I already took the limit of the cutoff equal to 0. And then this is physical distance can be made small, and then you take the limit. This limit is divergent, so it exactly reproduces the idea of what happens with a single entropy. It's divergent, but the way the divergences appear is completely universal. So the coefficient of the area term is universal. The coefficient of every term is universal here. But of course, the limit itself is divergent. But you can extract all the pieces in the expansion of the entropy from this idea.
Okay. Yeah.
Oh, sorry. So, well, then I was talking about this, the construction of the replica method. When you sew the cuts, here I put one cross. This cross is sewn with this other that have one cross. So it's the upper with the lower, the upper with the lower, the upper with the lower in a cyclic way. When you do that, you can realize that there is no more cut in the manifold. If you turn around this C1 curve, it will give you back to the same point, unless you do a curve around one of the boundary, around the boundary of the region. If you do that, and you end up here, and you do that, you end up here, and you do that, you end up here. So you have to do 3 times 2 pi angle to end up in the same point. So you have a conical singularity, which is called the conical singularity at the boundaries, while really the position of the cut, you can move the cut in the plane with the same boundary and nothing changes. So the cut is just apparent, it's not real. So if you are lucky and you can compute some particular path integral here for some of these replicated manifold, you can compute the entropy in the continuum, and you can do in many instances. But one interesting thing of this construction is that, in fact, these traces of O to the n are related to expectation values of operators. So it relates some information quantity, these range entropies, to expectation values of operators. And these operators are called twist operators. These operators exist for any global symmetry. So these operators are what somehow are implementing some global symmetry in a finite region of space. And you can always do that. This is always possible to implement a global symmetry in some local region. And in particular, in this case, this global symmetry is a global symmetry of permutations of copies. So you take a theory that is replicated n times, so it's completely uncoupled copies of n times copies of the same theory, tensor product of the same theory. And then it of course has an unbroken symmetry that is just permutation of the copies. And this twist operator is the twist operator corresponding to this symmetry. And you can do that the same thing. It's not something that's happening only for quantum field theory. You can do the same thing for just ordinary quantum mechanics. You have tensor product of two Hilbert spaces. You can construct the rangy twist operator for one of them, and the expectation value of this twist operator is just trace of rho to the n. I have some few minutes, maybe. Unfortunately, I couldn't reach the final part of my talk. I don't know, I have less than 10 minutes, right?
Yeah, I think, yeah, about 10 minutes.
Okay.
Of course, if there are questions, then, okay.
Yeah, there are no questions. All right, questions?
At the moment, I don't see.
Okay. So let me introduce these things that are important for the next lectures. If we take the replica trick for a special case, the special case is just half a space. So I take a cut going to infinity here, from the origin to infinity, and then you can see that the replicated space is just turning rounds around this point. So there is a symmetry, a rotational symmetry associated to this space. And in particular, if you take just the density matrix with one cut and one copy, you can see that the density matrix is just a Euclidean 2 pi rotation. You can compute it as a Euclidean 2 pi rotation between the boundary values at minus, phi minus, and phi plus, which are the entries of the density matrix. And then it means that the density matrix can be written as a 2 pi Euclidean rotation. When you go back to original Minkowski space, this density matrix is just a boost. It's a boost operator. Instead of a rotation in Euclidean plane, it's a boost operator. And you get the density matrix is e to the minus k, where k is 2 pi, the boost operator. The boost operator is something like the angular momentum. It's x1 times t0, 0, integrated all along from 0 to infinity. So we can always write the density matrix as an exponential of our Hermitian operator, and this is called the modular Hamiltonian. It's a compact way to write the density matrix. Is sometimes easier to write the modular Hamiltonian than the full density matrix. For example, here you can see that the modular Hamiltonian is something local in the stress tensor. And this is quite interesting because it tells you that the vacuum density matrix already has the information about the full theory. You have the T00, you can construct the Hamiltonian from this operator. So it's somehow similar to what I started with describing, that the vacuum has all the information about the theory. This is the modular Hamiltonian. In this particular case, it's local in terms of the stress tensor, but if you have other states or other regions that are not half a space, you will get something different. You will get non-local terms. You will get other operators in the modular Hamiltonian, and few cases are exactly known. And this is a very, very particular case because of this symmetry. And as we have written here, the density matrix in a thermal-like form, where this K is like kind of a Hamiltonian for the thermal density matrix, let's say, with the temperature 1. We can think also in the time evolving with this Hamiltonian, and this is called the modular flow. It's just taking imaginary powers of the density matrix, or putting an imaginary parameter here, evolving with the modular Hamiltonian. the interesting point here is that the modular flow is a unitary transformation of the operators in the algebra, and this unitary transformation can be used to define something like the density matrix, in the sense that this unitary transformation exists even in the case of algebras in quantum field theory, where the density matrix does not exist anymore. The density matrix in these algebras, because you have too many degrees of freedom, in the limit of the continuum, the density matrix does not exist, while the modular flow does, or the modular Hamiltonian does exist. So somehow replace the idea of a density matrix, the modular flow, the modular Hamiltonian, replace the idea of a density matrix in the continuum limit. Another way people used to say this is that this modular flow is a symmetry of the algebra, in the sense that if you evolve with the modular flow, the expectation value of this O tau is equal to the expectation value of O, because it's just, let's say, this operator commutes with the density matrix, so it will end up giving the same expectation value. But if you evolve in imaginary time, you will have this property, that is periodicity in imaginary time, and it's called the KMS condition. And so you can say that this unitary flow plus the KMS condition defines what can be defined as a density matrix in the continuum limit. So my time is over. I think I will stop here. Unfortunately, okay. I couldn't. Okay.
Yeah. So let's see. Okay, there is a question. Is the modular Hamiltonian part of the operator algebra of the region?
If you have a finite dimensional algebra, it is a part of the algebra of the region, but in the continuum limit, no, it is not. It can be defined. For example, here, what is well defined is the boost operator. So the boost operator will be the modular Hamiltonian, but it's a boost operator acting on the full space. It acts on the full space in this way. So it's not really an operator belonging to the algebra. But you can think always in the cutoff theory that it belongs to the algebra, that there is an operator doing this thing.
There is another question. What are the conditions on the density matrix in the cases that it exists so that the modular Hamiltonian is local?
The problem is that the term local is somehow attached to the idea of the continuum. I mean, local means it's an integral of some local field. So I don't know how to answer that in the discrete case. In the lattice, of course, you can think the same, but I don't know of any example of local modular Hamiltonian in a lattice. For example, if you have a lattice and I have half the lattice, it will not be local, because of the lattice will destroy this symmetry property that we have here.
And sorry if I may expand on my question.
Yeah.
So what I was thinking about was that maybe in the discrete case we can think of this. So I mean, the continuum case we define local in a way that it depends only on a finite number of derivatives, right? So in the discrete case, we might be able to define somehow a local operator by depending only on a finite number of near sites, for example, on the lattice, right?
Yeah. Well,
In
yeah,
that
it could
sense,
be.
is it possible to find some conditions on the density matrix so that, in the sense that I mentioned, the modular Hamiltonian is local?
Yeah, I'm not aware of anything like that. Yeah, I don't know. I don't know.
Okay, thank you.
Okay, so okay, don't see any other question. So let's thank Horacio again and resume in say 15 minutes.
Escape.
I don't see Mitat.
Yes, I don't see him.
Hi, Nadia. Yeah, first, can you hear me?
Yeah.
Okay.
Yes.
Yes.
Okay.
Yeah. Maybe you should. Yeah, now we should start, presumably, right? Okay.
Yes,
No,
yes,
no, no.
yes.
You still
Share
have,
the screen, yeah.
yeah, let me do share screen. Hi,
Yeah.
Nadia.
Hello.
Yeah, first, can you hear me?
Yeah.
Okay.
I see a black screen.
Yeah.
Black screen? That's not good.
You started screen sharing, but did not.
Okay, let me stop share and do it again.
Yeah.
Is there anything?
No,
No, no.
not so far, no.
Okay, let me get out of Zoom, get in again, and try again.
Mhm.
Sorry,
What?
try to share all your screen.
Um, Actually, what I am doing is that I am connecting my iPad with a cable to my computer, and I am sharing my iPad. And it says, trust this computer when prompted on your iPhone or iPad, select trust, but it doesn't prompt me for some reason. And it used to work fine. Okay, let me disconnect and connect again this thing.
We can also connect directly from my pod via Zoom, another Zoom account.
Then, you can see now.
Okay, now something happened, yeah.
Okay, now open GoodNotes. Okay, GoodNotes. Okay.
Okay, good.
And
Okay, so we can start with the Mitat
oh, wait,
lectures.
wait for me, please. I need to get water, otherwise I cannot start.
Okay. So hopefully we start with, we can start with Mitat lecture, the first of the 4 lectures. Yeah.
I have one more question. I thought we were starting at 8:30. Am I wrong?
At what?
15, supposed to be 8:15.
Oh,
Yeah.
Oh, I am sorry. Okay, let me start then. Okay. So
Okay, go ahead.
I am starting. Okay. Thank you very much. I am very excited to be at ICTP and delivering these lectures. And sorry for being 6 minutes late. It's my mistake.
Well,
So
no problem.
the title of my lecture is Semi-Classics, Adiabatic Continuity and Resurgence in Quantum Theories. There are 4 lectures, and the first lecture, I will briefly describe motivation, then discuss the exponential integrals. The motivation is whether we can make sense out of quantum field theories. We can define path integral rigorously, or whether there is a continuum definition of the quantum field theories. And here I start with a quote with Mike Douglas from his talk on String Math 2011, says that there is no essential difficulty in rigorously defining a Gaussian functional integral and in setting up perturbation theory. But he says most mathematicians would still consider QFT is still not rigorous, is because the standard perturbation theory provides only asymptotic divergent expansion. However, this is the whole situation is not as good as this. There are many other problems. Okay, so indeed there is this divergence of perturbation theory, asymptotic nature, even after regularization and renormalization. The standard tools that people use in asymptotically free theories, such as dilute instanton guess approximation, they no longer use it, but in the past it used to be used a lot. It used to be used a lot. And such an approximation is not valid because, instanton size is a moduli, and in dilute instanton guess, you assume that the typical separation between instanton is much larger than the size, hence the assumption is not meaningful. there is something called infrared embarrassment. One can read through Coleman's lecture. Standard results of large N is incompatible with the instanton gas and things like that. And there is a deeper problem called 2-3 normal on ambiguity. And the interesting thing is all of these things seems to be, when you understand things more deeply, seems to be related, okay? And we will use some set of tools, old and new, and some from mathematics, some from physics, and let me call it recent because some of them is not quite recent actually. Resurgence and trans series, maybe a little bit of complex Morse theory. And from physics, there is this notion of adiabatic continuity, which appeared more or less 13 years ago and still continuing to progress. And there are lots of things that we can do with gauge theories in locally 4-dimension, you know, by compactifying it differently on R3 process 1. So these are my tools. So I start with my lecture 1. And I will tell you a little bit about basic structure of the perturbation theory, resurgence, left-shade thimbles in only ordinary exponential integrals, and some of the most interesting lessons will carry over to PET integrals. Now, usually we consider you know, perturbation theory as an expansion in a small parameter, and in most interesting examples, either in quantum mechanics or quantum field theory, this sum starts to look better and better if lambda is sufficiently small, but eventually it almost always diverges as n factorial. So regardless how small lambda is, n factorial will always win and render this series divergent. So we learned that perturbation theory is a divergent asymptotic series, but we also learned that it works. For example, if you take QED, where coupling constant is 1/137, fine structure constant. If you look to magnetic moment of the electron, this is probably one of the best theory / experiment agreement ever. Remarkable at the remarkable level. And if you look to asymptotic freedom plots from experiments and as well as from theory, there is again quite remarkable agreement. Now, the universal behavior of the perturbation theory is actually as follows. So, and these things, this discussion dates back all the way to Stokes. So let's say these solid line here is exact result, this line. Okay, so and let's say this axis is order of the perturbation theory. So as you get higher and higher order, things starts to get better and better. So if you look to, let's say this is error. If you look to error, error gets smaller and smaller. But after some order that I denote as n star, you know, things starts to break apart. The error starts to blow down, gets larger and larger. So the one brilliant realization of Stokes is that there is an optimal order at which the error becomes minimal. Okay. So what Stokes does more than 150 years ago, you know, is that he truncates the series at this order, and this is called least term truncation or optimal truncation, except that there is an intrinsic vagueness to perturbation theory that you cannot obtain from the perturbative method. And this vagueness is actually important. Now, actually, if you try to estimate the order of magnitude of this vagueness here, you can estimate it by using Stirling's approximation for the factorial. You will immediately learn that this error is of order exponential minus 1/lambda. So it is an essential singularity at lambda equals 0, and it is irremovable. And so interestingly, the error that you get from perturbation theory is intrinsically non-perturbative. So that means that you cannot expand to a Taylor series in lambda. It gives you 0 plus 0 plus 0 plus ad infinitum. And so, oh, okay. Okay, I can skip this. And this was where Stokes standed a long time ago. And after almost 100 years, there is some, from math and physics, there is a number of improvement on Stokes' ideas. Okay. Now, this is sort of historical overview. But let me also say that from mathematics sides, from the physics side, these non-perturbative factors are extremely important because they describe tunneling in quantum mechanics, band structure in solids, which is of course related to tunneling, superconductivity, and our body masses, you know, the strong scale emerging from the strong dynamics, D-branes in string theory, so and so. Okay. So let me start with a discussion of an exponential integral. Okay, so let's say this is some prototype from zero-dimensional QFT, but it will turn out to have remarkable closeness to some discussions in quantum field theory and quantum mechanics and some semi-classical domain in quantum field theory. And we will see the reason why. And we will actually understand this example in great detail. So consider some potential of this form and consider exponential integral from minus pi over 2 to plus pi over 2. This is the potential. There are two saddles. Both of them are real, 0 and pi over 2. Okay. So on the real axis, if you go along the real axis, this saddle in this direction is a minimum. But of course, in the other direction, it's a maximum. That's the meaning of the saddle. And the other one is minimized in this direction, and it's a maximum in that direction. So it's a saddle. Okay. Now, here is the magic bullet. Okay. Let's say you expanded around this saddle one to perturbation theory. Okay. And there is this exponential of the action of that saddle. Then there are perturbative fluctuations, 1, 1/2, 9 over 8, so on and so forth. Okay. Now, you can also study perturbation theory around this saddle precisely. Okay. And you can estimate the large order behavior of A and 0. This is what I call dragon land that you deserted, you kicked out. Okay. Then you obtain an n factorial divergence. You obtain that the relative, the prefactor is A10. This is the relative action. A10 is action 1 minus action 0, but action 0 was 0. So this is 0. So this is really A1. So then you obtain this n factorial, n minus 1 factorial, n minus 2 factorial, and you say, these numbers here, as you can see, are in precise agreement with these numbers there. And remember, this is large order of the perturbation theory, the part that you throw away. Clearly, the divergence of perturbation theory is not just a nuisance. It is not something to be ignorant about. It is actually concrete information, coded information about the structure of the perturbation theory around the other saddle. This is what we learned. And this structure that I have drawn here is crystallized by Berry et al. Fairly recently in the 90s. Okay. Now, here I borrowed a slide from some remarks from Michael Berry from 50th year celebration of the ICTP. And he points out that, you know, there is a rebirth of these ideas in semi-classical analysis and the divergent series. And Now he says, from the final part, to my great surprise, there is another rebirth. Appears to be in applications in QFT and string theory. But now he also remarks, the difficulty, the technical difficulty here is immense, because it is not just a question of one integral, double integral, quadruple integral. Even in quantum mechanics, PET integral, we have infinitely many variables and infinitely many exponential integrations. And he remarks that things can well be different there. Remember, this structure here was the structure that you obtained from one ordinary exponential integral. But now, let me tell you the results of a PET integral and infinitely many exponential integrals. Now, let's say you consider a periodic potential, you know, some, sorry for being a little bit sloppy, periodic potential like that. And we learned that large order of perturbation theory again diverges as n factorial, and n factorial divided 2 times the action of the instanton, and there are corrections, n minus n factorial, n minus q factorial, so on and so forth. Okay? In this system, I will discuss this, there are actually critical points at infinity. These are instanton anti-instanton configurations. But they can be actually described as exact saddles, but these exact saddles has a special role. In the past, you know, instanton anti-instanton confused a lot in many physicists, you know, led to many confusion in many physicists, but we understand them very precisely now, what they means. And we can calculate what they give as well as fluctuations around them. Okay? Now, look at these correspondence. So again, these n factorial divergence is there, and with the 2 times the action of the instanton, and this part is there. And this part is the story that had been revealed by Bogomolny and Zinjustan in the early 80s, but to my mind, it is not sufficiently appreciated at all. There are some reasons for that, but set that aside. And these terms, the fact that this structure survives, the overall structure survives as you expand in the weak coupling expansion around the other saddle, this critical point at infinity, as well as when you look at the asymptotic nature of the perturbation theory, you can calculate these things completely independently. This structure survives is obtained fairly recently in 2014 in these integrals. And now we are supposed to ask, why is this happening? One of them is ordinary exponential integral, the other is infinitely many integral. And I can assure you similar structure also holds in semi-classical domains of quantum field theories. Okay? So one remark is very insightful, very deep remark is by Ekal himself. He says that resurgent functions display at each order of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up in a slightly disguised different guise, as it were, at their singularities. It literally describes the phenomena that's happening here. Okay. Now, remember, at the beginning of my talk, I asked whether we can make sense out of continuum, we can make sense out of quantum field theory, continuum definition of quantum field theory. Now I want to ask a simpler question. The question is, can we make sense of a semi-classical expansion of quantum field theory? Let's say that it admits a weak coupling semi-classical expansion. Can we define it properly? For whatever it is worth, whenever we try to construct some observable, okay, we will have some perturbative parts, we will have instanton contributions, and we will have perturbation theory around instantons. And all series appearing above are actually asymptotic divergent series, generically speaking, unless there is a good reason not to be so. And this kind of structure, which is a series of the series, is called trans series, following resurgent terminology. And the interesting thing that we will come to understand is that this trans series is a well-defined object under analytic continuation. Okay? And all of these coefficients are related in a precise sense, as I have shown in the earlier example. Let us try to understand the mathematics of this system a little bit better. So I will just briefly describe Borel transform and Borel resummation to get people familiar with, but it will look a little bit like a black box at first. But then we will geometrize what Borel transform and resummation means, and it will make much more sense, okay? So we start, as usual, with a divergent asymptotic series where AQ is blows up as Q factorial eventually. Then Borel transform is defined as this dividing, you know, the A sub Q with this Q factorial and defining a series in the T plane, complex T plane, okay? And usually this object does have a finite radius of convergence, okay? We define Borel's resummation of this series as a Laplace integral. And in the old physics literature, it is defined as a Laplace integral from 0 to infinity of this transform thing. And if this BP of t has no singularity in this direction on R plus, then we say that this B of G square is the unique Borel resummation of the perturbation series. Okay? But very often, there will be singularities in this direction. And you have to go around these singularities. You have to avoid them. You have to go either above or below. But this will give you a real part, which is principal value, and some ambiguous imaginary part, twofold ambiguous imaginary part. And in quantum mechanical example, this ambiguous part will be non-perturbative, and it will be 2 instanton factors. Okay. This non-equality of the left and right Borel resummation means that the series is not Borel summable, it is ambiguous, and a measure of this ambiguity is something called Stokes automorphism, or jump of this sum as you cross this singularity, as you go from this way to somewhere like that, as you go from here to there, okay? And that jump will be proportional to these exponential factors, okay? Now, what I described is this triangle. You start with a series, a transform, and a Laplace integral, which is the sum. But we learned that in general, in Borel plane, there will be a bunch of singularities. And if we do this directional Borel resummation in some direction in which there are no singularities, then everything seems to be good, okay? But if there is a singular direction like this or like that, it naively looks like the following. We had a pathology in our system. We had a disease. And the disease was, perturbation theory was asymptotic and divergent. But now we traded that disease with another one. So instead of having divergence, we have twofold ambiguity. These things, twofold ambiguous result. It is finite, but twofold ambiguous. Furthermore, we started with some real series. This ambiguity turns out to be purely imaginary. Okay? Now, of course, we can ask, why is this happening? What is happening? Are there any questions about Borel resummation and things like that?
Let's see. Yes, there is a question here. Let me read it. Are these singularities or cuts? Question mark. Can you not choose to avoid some poles from above and some from below? Thanks.
These can be poles. These can be branch cuts. Both of them are possible. Generically, they will be branch cuts. If there is a pole, again, there is a good reason. But it is still, but in order to define the physical theory, unfortunately, I am, I hate to break the news, but whenever you are doing expansion, for example, in quantum mechanics with, instantaneous tunneling, we are always on this line. We always have to define these integral properly. And there will be an intrinsic ambiguity here. And we will also learn how to fix that. This is something unavoidable. The result is twofold ambiguous. Okay. Now, this is one side of the story. It is analysis. I sort of gave a overall picture. In my lecture notes, they are written in much more detail. Now, I want to go to the other side of the story related to geometry and topology of this space that we are doing integration and related to this exponential integral. So at the end of the day, we are considering an exponential integral of this kind. For for ordinary integral, we are considering some integral ds dx exponential minus s. So when we are dealing with such an integral, exponential integral, the first thing we do with the saddle point method, the first thing we do is to determine the critical points. These are determined by extremizing the action. These are the.
Let me specify the previous question. Maybe there is an additional, but it seems that for n poles, there are many more ways to avoid them than just two.
Yes. That's absolutely correct.
So
the remark is absolutely correct. Indeed. There are probably 2 to the n ways to avoid it. It's a right remark. And the formalism we will describe will actually fix that.
Okay.
And that's again something physical and geometric that can be understood. If time permits, I will show an example. This is a very good question, actually. Okay, so as I said, there are critical points, and attached to each one of these critical points, there is a cycle, which in one-dimensional examples we can call, steepest descent cycle, but in multidimensional examples, these cycles are called Lefschetz symbols. Okay. Now, the interesting thing that you may not know from, a class in mathematical physics is that these symbols that you attach to these critical points can be thought as forming a basis over a vector space. If you have an integral, some integral over some cycle, it turns out that you can express any cycle as a linear combination of these symbols, and these symbols form a complete basis for integration. Okay, and sometimes this is called homology cycle decomposition. Okay, how do you determine the symbols? The symbols are determined by something called complex gradient flow equations, or Picard-Lefschetz equation. Okay, these things, these structures. Okay. But for our purpose, one thing that's quite important about these symbols is that if you look to the imaginary part of the action, if you ask whether it flows or not, you discover that the imaginary part under this gradient flow time is actually invariant. So there is an invariant associated with the symbol, and this is the phase. This is the imaginary part of the action at the critical value. So the action at the critical value, its imaginary part determines the phase over the whole symbol. Okay. Now,
what is tau?
Tau is the gradient flow time.
Time. And the Z's are the ZIs are what? The
ZIs are the complexification of
axis.
Yeah.
Okay.
So the point is you complexified everything. So if you are starting, as I said, okay. So if you start with something like R to the N, you move it to C to the N, but these symbols, J sigma, live in middle dimensional space. So you do not introduce extra degree of freedom because dimension of these symbols is still N. Okay.
Okay.
So thank you for the question. And the other thing is, with my definition, I wrote the exponential integral as exponential minus s. You can actually immediately prove that the real part of the action is always growing. That means that this exponential minus s is always decreasing. Because of this reason, this cycle is also called steepest descent cycle, and the method is sometimes called steepest descent method. So this property guarantees that the integral over the symbol is convergent. Actually, I will describe to you semi-classical method as an exact method in the ordinary integral. And very likely it's also an exact method in quantum mechanics and possibly in the semi-classical domain of QFT. But in the last remark is a guess. Let me skip this page. It's not that important. But now let us go back to our example. We said that there are actually, let me go back. Let me move to this one first. There are actually two critical points. One of them at 0, the other one is at pi over 2. Now, lambda was coupling constant. If you take argument of lambda to be 0 minus, you can actually solve this gradient flow equation. And you find that it starts in this domain, continues like that. Oops, this is not a good color. It starts in this domain, continues like that, and comes back to that domain. Okay, this is the symbol associated with the cycle rho 0. Okay, and for rho 1, the symbol goes up like that. If you are at argument of lambda 0 plus, then this J0 symbol starts down here, goes up there. Only this domain is same as in orientation and everything with this, but the tails flipped. But this part, the symbol associated with J1 is still the same. J1 0 minus is approximately the same as J1 0 plus. It didn't change much at all, okay? Now, that means that if you want to write original integration cycle from minus pi over 2 to plus pi over 2, exactly at the for argument of lambda being 0, there are actually two different ways of writing it. One of them is to write it like that and go up like that. The other one is you start here, okay, and end up there, okay. The other one is you start here, go down, come back, and end up there. This is happening at 0 minus. This is happening at 0 plus. So you learn that at argument of lambda equals 0, this integral in terms of Lefschetz symbols has a multifold ambiguous description. But it is obviously clear that regardless of which description that you use, this integral will be just integral over this segment, because this part exactly on the line, this part, you can carry over this segment here to here. This part plus J0, oh no, minus J1, the tail. Actually, the tail of J0 turns out to be exactly like, oops, sorry, for J1, okay? the tail of J0 is exactly like J1. So they are destined to cancel each other, okay? So I hold my promise, you know, there are two saddles, two cycles, okay? One of them you can call perturbative cycle, H0, the other you can call non-perturbative cycle. And the original cycle from minus pi over 2 to plus pi over 2 has two different representation in terms of tymbals. But when you are away from the tymbals, when you analytically continue, for example, you go to argument lambda being 0 minus, there is a unique description. It starts somewhere like that, ends up somewhere like this, and these things makes a move like that. But now, here is the interesting thing. So in this process, two things jumped. First of all, the integration cycle, J0, 0 minus and 0 plus are different. So the original integration cycle associated with the rho 0 critical point, it jumped. But also the coefficient of J1 did not jump itself. The cycle J1 did not jump, it did not change. But its coefficient also jumped. This is something called Stokes phenomenon. But these two jumps came in a correlated way. But when we are dealing with semi-classics, we are only doing an integral. So when we are doing an expansion around one critical point and doing a Borel resummation associated with it, we are only considering the contribution of this saddle, for example, of one of the saddles. So you can, as I said, you can go above and you can go below. There is a real part and there is an imaginary part. You immediately associate this choice, this thing, this C plus minus is flip of tail of the cycle. Okay. Now, these Borel ambiguity, which comes from left and right Borel resummation, is really the ambiguity of the integration cycle at that point. So this is interesting because we also see the cure of the problem, the cure of this ambiguity within the same problem. If I define the integral cycle exactly in this way, this combination or that combination, the sum of the two will be ambiguity free. So you can do the following. Geometrically, this integral is sum of two tymbals, okay? You can also write it sum of two exponential terms with perturbation theory around them, okay? Now, the important point is this thing, these tymbals are piecewise continuous. As you change theta, for example, they change continuously.
Sorry, Mitat, maybe
Yes.
if I'm not, it's not appropriate, I don't know. There is a question by Berad Tagavi. Yeah, maybe he can.
Sorry, can you go back to your previous slide, the one you had yes, exactly. When you're talking about the tails canceling, you're talking about those tails that are close to each other, right? But we also wanted to start from Z, I don't know, it's Z minus 1 or minus L.
Yeah.
And but what I'm saying is that we wanted to start on the real line and end up on real line. But with those contours, we are starting at minus ZL plus infinity times times I, right?
Okay, I can answer your question immediately, actually. So even if your integral is on the real domain, in general, the tymbals will live in the complex domain, okay? And you can write down that integral over the real domain as a linear superposition of the tymbals which live in the complex domain. So indeed, the integral is from in this real domain, okay? But you can write it as exactly when argument lambda equals 0, you can write it as sum of these two timbres, you know, this one doing like that, and this one doing like that. These things, these parts cancel each other. These parts cancel with each other.
Yeah, my question was exactly that. Is it obvious that the two ends above the contour cancel? Is it obvious that they cancel?
They do cancel. Okay. Is it obvious? Actually, it is obvious because in this case, this system has a pi translation. Okay, and I can carry over. I actually use that. I can carry over this cycle here to there. Okay, so these are really, these tails are actually identical. So the tail part is destined to cancel because I can carry one of them over the other. This kind of things is even, you know, easier looking in the polynomial potentials. And I have an example like that, but for the sake of time, I removed it.
I see.
Yeah.
Okay. Thank you.
Thank you. Okay. So we learned that there are multiple interesting things. These timbres are piecewise continuous, but it is discontinuous at the Stokes line. Okay. The coefficient, the multiplier, are piecewise constants, but again, these piecewise constants are discontinuous at the Stokes line. This +1 here became -1, for example. Okay. And okay, and these two discontinuities, there are two discontinuities in the discussion, are present so that the sum, the integral expressed in this Lefschetz-Timble decomposition is actually continuous. Actually, this is in certain respects, yeah, very intriguing part of the story. There are discontinuities, but discontinuities are there to make something which is supposed to be continuous, continuous and meaningful. Okay. Now, let me go to a little bit more detail now, discuss the connection of this geometric picture with the Borel analysis. So if we study perturbation theory around this saddle 0, the exact formula, we can obtain exact formula. This is such an easy integral. We can obtain exact formula and it diverges as n factorial lambda to n. And it has a divergent piece like that. And if you do a Borel transform, this object actually can be written some hypergeometric function. I don't know the name. It's not that important, like that. Okay. Then you can do Laplace integral. So if you look, there are two saddles. You write row 0 and row 1. If you look to phi 0 and Borel plane associated with it, so this thing, phi, it will have a singularity on positive real axis, you know, on R plus. And since we want to define our theory at argument lambda equal 0, we want to define our theory there. This is the structure that we have to understand. On the other hand, on the flip side, if you write down the series phi 1 and Borel transform of that, phi 1 is a function of time, and you can see that it also has a finite radius of convergence. This object has a finite radius of convergence in that case, but the singularity is on R minus. And you wouldn't, at this stage, you wouldn't care about it, but more generally speaking, you should. Okay. Now, let us do the following interesting thing. Let us do the summation over S plus. A friend asked if this was a cut or pole, the nature of the singularity. In this case, it's a cut. And the cut starts at 1/2. And you can go above or you can go below. And do the summation from above, do the summation from below. Okay. And let us look to the action of these objects to the original series. Okay? You can do this manipulation, and this discontinuity, you can write it as a Hankel integral, okay, in this form. And by using some identity related to hypergeometric function, you can actually show that discontinuity in the Borel resummation of this object is related to the action of this other saddle and the perturbation theory around it, okay? This is the punchline of the resurgence, but in a very, very simple example. You have a number of saddles and a number of perturbative series around them, okay? And the discontinuity of the Borel resummation of a series Vm associated with the saddle rho m is determined only by the other series in the problem, Vn associated with the other saddles, and nothing else. This is a closed system. You can look to any left-right resummation, and on the right-hand side, you will always obtain a perturbative series associated with one of the saddles in the problem, okay? This is very interesting. So this operation is closed, okay? So this is the essence of resurgence. And all of these series around all saddles are closed under Stokes jumps. And Ekal defines something called singularity derivative or alien derivative, such that, for example, this alien derivative acting at 1/2 on P0 gives you some constant. In this case, it is 2i P1. P0, P1, exactly. Or similarly, delta minus 1/2 acting on P1 will give you minus 2i P0, something like that, okay? Now, let us describe Borel-Ekal resummability, because we see that Borel summability is not sufficient tool. So Borel by itself, not sufficient, but Borel-Ekal is good, okay? And we will derive some exact results from semi-classics. Again, this is a very easy integral, but this discussion will also hold in very non-trivial examples in quantum mechanics and some semi-classical domain of QFT, okay? So we write down the partition function as a two-term trans-series. One expansion around perturbative saddle, the other expansion around non-perturbative saddle. And these things, these coefficients change as you change the domain. On the other hand, Lefschetz symbol decomposition was this. It was this plus that, and the other one was, this one was this plus that, okay? And now, if you do Borel-Ekal resummation, okay, let's say you do it approaching argument of lambda at 0 minus, okay? You do resummation of this, you do resummation of this, but this object is Borel summable. Phi 1 is Borel resummable. So this part, do not worry about, but this part, you'll have an imaginary term like that. And it will turn out that there is a real part and the imaginary part coming from the original cycle will cancel with this exponentially small term coming from the other saddle in the problem, and the result is real and unambiguous, okay? And this result is actually exact. As I said, you can do this integral exactly. It is real, unambiguous. There is no imaginary part. There is no ambiguity. There is no pathology. And this is a simple realization of Borel-Ekal summability. Any questions?
I don't see.
Okay. Now, let us go back to our original amazement with the, with the relation of early terms, late terms, early terms around.
There is a question, sorry. Where are the instantons you mentioned? Question mark.
Okay, very good. These are actually zero-dimensional examples, okay? There are non-perturbative saddles. So, of course, instantons are present in quantum mechanical system as well as in quantum field theory, but here the replacement is following. If you look to this saddle here, its contribution is exponential of S0, but the action is 0. So, and there is a perturbative fluctuation around them. This is perturbative saddle. And this critical point here, these are Gaussian critical points, it gives a contribution S1, which is exponential minus 1 over 2 lambda. This is the counterpart of instanton, counterpart part of the instanton contribution, which is exponentially small. So this non-perturbative saddle plays the role of the instanton. Okay. Now, remember, originally...
Then there is another question. What about minus pi over 2?
Oh, this is actually the thing that I have written down here is you can either think that both of them are contributing as 1/2, this one and that one, or since this is periodically identified, you can think integral, from infinitesimal neighborhood of minus pi over 2 to here. But you can put a factor of 1/2 count both, or just count this one with an overall factor of 1. That's not a problem.
Okay.
Now, remember the original perturbation theory, this thing was something like, okay, a and 0 lambda to n, and its large order behavior was factorial, but these coefficients 1, 1/2, 9 over 8, 7.
Sorry, can you accept another question?
Yes, of course.
This is why in general we expect the Borel resummation to give the exact result and not just a non-ambiguous one?
Oh, in this case, because of the geometric construction that we did, okay, so let me go back. This cycle here is exactly equal this plus that, okay? And this thing, and in this sum, as I said, this part cancels with that part. This part here cancels with that part, okay? They are overlapping. Sorry for crowding the page. So it is destined to give the exact result. The surprise is, in some infinite dimensional examples, PET integrals, we are sure that the same mechanism also works. That's the surprise, okay? In these ordinary integrals, it's not a surprise. From the geometry, from the topology of Lefschetz symbols, we see very concretely it is the case, okay, in these simple examples. And it's just, this part is really just that segment. It's the integral. So the real surprise is in the infinite dimensional integrals. Okay, I described this, described that. Okay, but now, as I said, this large order factorial divergence is controlled by this relative action A10, which is A1, action 1 was minus action 0, but action 0 is 0, so it is just A1 in this case. And there is n factorial divergence, n minus 1, n minus 2, so on and so forth, okay? And the coefficients here are coming from perturbative contributions. And you can ask the following question: why this had to be so? Okay, because this was our first empirical observation. And the reason is you have to use two facts. One of them something you probably know from complex analysis, Cauchy's theorem. And the other thing is by using this discontinuity of this P0 being related to P1 and non-perturbative factor. Now, let me go back to this nice figure and let me do a cheat. Or I can draw it again here. So here, we have seen that there was this branch, and I can do a Cauchy integral like that. Okay, so let me see the orientations. Okay, something like this, and make sure boundary does not contribute. And you can use, by using Cauchy's theorem, you can actually write f of z, you know, if you wish, you can write it the omega f of omega minus z, z is some point here, okay, 1 over 2 pi I. You can write it like that. This closed integral has to give you f of z, obviously. And you can massage this integral, Cauchy's theorem, in such a way that you can bring it to this form, that the right-hand side is only a sum over this Hankel contour. And actually, if there are multiple directions in which you have singularities, for example, if there is another direction, then you have to do a summation over all of them carefully. But in this case, we only have one direction in which we have singularities. And you can write this factor here, this continuity, by using this formula and calculate integral order by order. And now you see that, look, pay attention. We are calculating large orders of perturbation theory around saddle 0, and they are dictated by this relative action and the contribution of the perturbative fluctuations around saddle 1. So the information in the series expansion around this non-perturbative saddle surges up, appears again in a disguised form as an expansion around the perturbative saddle and vice versa. Okay. Now, how much time do I have?
5 minutes.
5 minutes, okay. And okay, so this story I told you in a simple exponential integral, okay, exponential integral. It is very nice, but you may think at the end of the day, this is just an integral, okay? And this is something that we can do exactly after all. But I showed you that semi-classical method in this example, at least in this class of examples, is something that can be made exact. That's important. It's not an approximation. It can be made exact. Even in quantum mechanics, we have infinitely many coupled exponential integrals, and in general, infinitely many saddles. Very similar structure will hold. Now, it turns out that there is a genuine universal behavior associated with the structure in this Borel plane, okay? In this story I am telling you. So it does not quite matter if you are dealing with exponential integral or PET integral or QFT. As long as their Borel plane data are same, it is literally same problem. This change in the number of saddles, you know, the number of saddles may become infinite in PET integral, for example. But for closely knitted saddles, the saddles which are close each other and which talk with each other, it's important that there is some intersection number or talking, literally, let me say talking. Integral or there is a, okay. So for these closely knitted saddles, this discussion from quantum mechanics, from exponential integral will carry over verbatim. And these ordinary integral will provide an extremely useful prototype, okay? Now, I want to mention one more example, and this is very fast. And I will ask students to go over it on their own time, on your own time, okay? So this is sort of a homework. On your own time, fill in the blanks, okay? Blanks here. So let us consider another exponential integral, which is some Jacobi elliptic function. I chose this example intentionally because it's a doubly periodic potential in the complex domain. There should be Z, okay. So it has this function, if you look at it, I will consider this as my partition function, okay? And I should have a figure, sorry about that. It is a doubly periodic function. One of the period is 2k, and the other period is 2ik prime, okay? And there are, if you look to the critical points, there are a number of critical points. So you can go ahead in this problem and calculate perturbation theory. And if you, and there is a parameter here, m. Actually, if m is equal 0, this is probably sine square. And if m equal 1, this is probably sinh square, okay? Yeah, this is the construction. It goes from sine square to being sinh square. So in general, for a general m between 1 and 0, it has both real critical point as well as complex critical point. You can go ahead and calculate perturbation theory around the perturbative saddle. Here you see that around 0, it is a non-alternating series. Around 1, it is an alternating series. And at 1/2, there is something interesting happening. All the middle terms vanish, so and so. Okay. You can ask, what is the role of instanton and other instanton? In this example, it turns out, let me immediately tell you, there are 3 saddles, okay, that are important. One of them is perturbative saddle, the other is a real saddle, and the last one is a purely imaginary saddle. And you can show that the large order of perturbation theory around this saddle is solely dictated by other saddles in the problem, B saddle and C saddle, okay? So this is a 3 saddle problem, and you are looking to the perturbative saddle only. Hence, it is a 3-term trans series, okay? And the perturbation theory around saddle A here is dictated by both B and C. So this kind of structure actually is interesting because if you look to Borel plane, it has a singularity both on R plus as well as on R minus. Okay, so if you want to do this, if you want to derive this formula from complex analysis, so you have to take care both of these cuts into account. So go around them, something like that, and do something like that. But having these singularities both on R plus and R minus is something that mimics the structure of something called UV and IR renormalon in quantum field theory. Now, this is my last 2 pages. Let me just focus on this page. Now, if you look to the importance of the saddles here, this one gives you exponential plus 1 over lambda. This one gives you exponential of 0, and this one gives you exponential minus 1 over lambda. Okay, this is C, A, B. These are the saddles. Okay. Now, for the least dominant saddle, there is no Stokes jump, because when it flows, you know, it cannot change abruptly. But this one is the counterpart of our sine square. You start from here. The original integration cycle is like that, but the timbals are like this. And it can, I only put here the Stokes phenomenon. And these are the characterization of these Stokes jumps. So you can actually study Stokes phenomena. JB cycle does not jump, and JA cycle jumps like that, and JC cycle jumps by 2 other exponential factors. So this is a useful example, and I encourage the students to work the details of this on their own time. And I can take some questions now.
Okay. Well, I think since we are a bit over time, and there is anyway the tutorial today, right? Maybe we can
Right.
postpone questions to that session, right? If there are no urgent questions now.
If there are no urgent questions, that's fine. And there were already questions during the,
Yeah.
the talk.
Yeah.
So.
In which case we resume at 5 o'clock Italian time, which is in 1 hour, 35 minutes, more or less. Okay, thank you.
Thank you.
Thank you.
Thanks. Bye-bye. Okay. Okay. Sorry for being this 5 minutes late.
No problem. I mean, that always happens. There are always.
The reason I didn't check the schedule, I was 100% sure it was 8:30 because you know, in my time, because my kids' school starts at 8:30, and we were debating whether it should be at 8:35 or 8:30.
I see. Okay.
CCP.
No, it's okay. Yeah. And yeah, the tutorial, just to remind you, is again, yeah,
yeah, it is
6:15. Yeah,
Gosh.
15 is always the.
Yeah. It's my mistake.
Yeah.
Okay. I at some point requested whether it can be at 8:35. Okay, my time. And my mind went to the fact that the school starts at 8:30, and you know, now it is online system, they can start and I can come here and start. Sorry about that. Tomorrow I will be on time. Okay.
No, it's okay.
That's not a problem.
Not a problem. Thank you.
Okay. Thank you very much again.
Thank you. Yeah.
Bye. Leave. Bye.
Bye.
Hi, Clay.
Hi, can you guys hear me?
Hi, Clay.
Everybody hear me okay?
Yes.
All right, good. Sorry, it took me a minute to figure out the Zoom link.
We're on time. So
Barely.
do you have everything you need?
Yes, I think so. I am able to share screen. Let's see. Okay.
Yeah, we can see that.
Very good.
Hi, Clay.
Hi, how are you?
Hi.
Hi,
Good
Clay.
morning.
Hi.
You are in your office, it looks like.
I know it's quite the luxury these days.
Running away from kids or something like that.
Basically, yeah, you can come in your office and shut the door. That's
Yes,
the
okay.
status here. But I mean, practically speaking,
He wants to learn wormhole.
Sorry? No, go ahead. Somebody said something.
oh, I was just saying, practically speaking, the lectures I think would be extremely interesting if I did not have access to my office.
They would be more entertaining for sure. Unfortunately, I'll have to miss your lecture tomorrow. But
That's okay.
sorry, some unavoidable meetings, I'll have to miss some of your lectures.
What title did I give for my lectures? Intro to Generalized Global Symmetry, something like this.
Yes, hold on, I'll tell you.
I mean, I guess I can make up a new one right now.
It's Introduction to Generalized Global Symmetries and Anomalies.
Okay.
Yeah, it was something about black holes.
Enough of that. You guys have had million lectures.
Yeah, yeah, we have many lectures. Very good ones. You know.
So Clay, you ready to start?
Sure, I think so.
Okay. So welcome back, everyone. We've got a new course starting now, given by Clay Cordova from Chicago. And the title is Introduction to Generalized Global Symmetry and Anomalies.
Okay, thanks very much for the invitation. The lecture, the first ICTP virtual school. And I hope that we can try and mimic as much as possible the usual interactive format. So please chime in with questions if you have them. I'll also try and take some designated breaks for questions. Okay, so today's lecture will be kind of a little bit of a broader overview. We will try to give motivation for these topics and illustrate, at least in words, one of the main results that we're going to be aiming towards. Okay, so let me start with a basic QFT question. So a basic QFT question is just about the renormalization group. So we'll imagine that we have some UV quantum field theory, which is given. This could be some, say, asymptotically free gauge theory, or some lattice model, or maybe some other construction. And then we do something to it to trigger an RG flow. And we want to know crude properties about the infrared physics. I mean, ideally, we'd like to know everything about the infrared physics, but in these lectures, we'll settle for some crude properties. And generally speaking, the motivation for these lectures and these topics is to give some new tools that are useful in this very general setting. So that sounds very abstract, but let's zoom in on a example. So examples that we really want to make progress on will be gauge theories, in 3 space-time dimensions. We'd like to study all kinds of QFTs, but really concretely, these are the holy grails. And let's discuss now and Yang-Mills in 4 dimensions. So here I mean no matter. So let's discuss this kind of problem. Probably many of you have seen this before in QFT class, but I will use this to highlight some of the basic techniques and kind of results that we're going to be able to prove. So what's here? What do we believe about S-pure Yang-Mills? Well, the lore is that at long distances, that is in the IR, the theory is gapped and confining. For instance, you may have seen that the theory becomes strongly coupled. At a scale lambda QCD. And we believe that all the masses of particles in the theory are of this order, lambda QCD, and are greater than 0. So that's what we mean when we say gapped. We mean that the particle masses are greater than 0. And confining, well, that has to do with the color charge. I believe all massive excitations are color neutral. So that's supposed to be striking, although we become familiar with it in high energy physics. It's supposed to be quite striking because at high energies, there's these colored gluon degrees of freedom, but at low energies, they disappear. Okay, let's spend some time elaborating on this. So the action Mills theory contains a very interesting term. This term takes the following form. So it's the theta term. And this quantity here is sometimes called the instanton density. And if I've gotten my factors right, the integral of trace f wedge f over 8 pi squared is quantized. So that means this parameter theta, which is a kind of coupling constant of the theory, we can think of it as being valued in a circle. So it's periodic. That's of course
we have
because
a raised hand.
okay, don't raise your hand, just start talking. I can't monitor the hands.
Okay. Yeah. So my question is, you said that obviously the lower is that in IR Young-Mills is gapped and confining. So I was wondering about this and confining part because, for example, in Jaff and Wheaton's statement on the clay millennium problem, I think they only say gap. So, I mean, wouldn't gapped automatically imply confining? I mean, probably just a stupid question, but
no. In fact, part of the purpose of these lectures is to disentangle all these notions and figure out what's independent from what else. So, in fact, gapped does not imply confining.
So, I mean, so just proving that Young-Mills' gap would win someone $1 million without having to prove that it's also confined.
Well, I haven't read the fine print on that clay math problem that you're referring to, but it sounds like you have. So I guess the answer is yes.
I see. Yeah, I mean, probably I've missed a whole lot of details, but anyway, thanks a lot.
No problem. Any other questions right now? Okay, so let's keep going. So we have in Yang-Mills theory, in addition to the Yang-Mills coupling G, which is becoming strong at long distances, we also have this periodic coupling theta. And it's natural to ask, how does the IR depend on theta? And maybe your first instinct might be to say that it does not depend on theta. After all, you know, theta controls this instanton density. That doesn't really enter the perturbation series. It doesn't really enter the strong coupling scale. So you might be forgiven for thinking maybe the dependence on theta is very boring. And one of the things I'm going to do is to convince you that that's not the case. Okay, so in order to keep going, it will be useful to develop some lingo that will help us organize the IR of QFTs. So I'm going to introduce some terminology.
There's another question, sorry.
Yeah, go for it.
Hi. Yes, one question. When you say that the IR is gap plus confining, you're assuming some specific action, for example, the usual Yang-Mills action, or you would say that this will happen for any type of action with certain properties in the ultraviolet, or can you expand on that?
Well, it's a question about the universality class. So when I made the statement here, you could think that I meant it narrowly just about the Yang-Mills action, trace f wedge star f, plus maybe some irrelevant operators that you use to, but that's really what I meant.
Okay, thank you. Thank you.
Okay, so we like to organize the infrared of quantum field theories into very, very coarse universality classes. So, okay, so what's the first one? The first one is gapless. So I discussed that Yang-Mills, we think it is gapped, but what does it mean? What's the opposite? What does it mean to be gapless? Well, that would mean that the long distance is described by a CFT. So this CFT, it could be free, as in some free theory of massless particles, or interacting. So that's the first coarse universality class that we'll introduce. And the second one that we is gapped. And let's say again what we meant. So first we meant that particle masses m are all greater than 0. But we can now, if we're in this gapped universality class, there are two interesting subcases to discuss. What are the subcases? So the first is probably what you naturally think of when you first encounter the term gapped, and that's what's called trivially gapped. What does that mean? That means that the IR at sufficiently long distances is empty, i.e. the trivial theory. So there's no correlators at all. In other words, the infrared just consists of the single vacuum state and no fluctuations at all to discuss. But a second, richer possibility, if your theory is gapped, is that the theory could be a topological quantum field theory. For instance, not in this space-time dimension, but in general, and it might be 3D Chern-Simons, or maybe some 4D TQFT if we're talking about 4D QFTs. And here, this would mean that there are topological correlation functions. So these are some broad universality classes. We can have gapless and we can have gapped.
Sorry.
And yes.
Can I ask, when you say trivially gapped, do you mean like the correlators go like exponential of minus mass times the distance, or like, is that what you mean?
No. So that's just, so the question was about what does trivially gapped mean? Does it mean that the correlators decay exponentially with distance? In fact, that's true just if you're gapped.
Yes, but then like what is the distinction between these two? I'm like not sure I understand.
Okay, good. So, well, have you ever studied 3D Chern-Simons theory?
I mean, a little bit, but not in any detail.
So in, say, 3D Chern-Simons theory, there are Wilson line observables, and the correlation functions of these observables don't depend on distance. You can separate them or move them together, and the answer will, for the correlators will be the same. So one implication of that is that correlation functions of local operators, the clustering that you just discussed, would always factorize into product of one-point functions.
I see. Okay.
But in both cases, they factorize. It's just in one. Another way to see the difference between trivially gapped and richer topological quantum field theory is to imagine that space is a more interesting manifold. So usually when we're discussing quantum field theory, at first pass, we're always thinking space is just R3.
Yeah.
But imagine space was interesting, like a 3 torus. Then you could ask, how many states are there in the theory? And the trivially gapped theory has the feature that no matter what space, what kind of spatial slice you choose, there's always exactly one state. On the other hand, the topological quantum field theory, the number of states in the theory depends on what the spatial slice is.
I see. Okay.
That's another way of saying what the difference is.
Okay, thanks.
No problem. Okay, more questions. Okay, so
sorry, I just want to ask one thing.
Yeah,
So are you saying here that the topological quantum field theory in 3 dimensions can arise from Yang-Mills theory in the UE if you flow down in the energy scale? Is that one of the possibilities?
Indeed. So let me. I think this question will be answered in the next couple minutes. So let's ping me in a couple minutes if it isn't. Okay. So we have this lingo, and now you could ask, okay, Clay, what is the actual lore about Yang-Mills theory? Say SUN Yang-Mills theory. And well, the really more precise conjecture. The more precise conjecture is that SUN Yang-Mills at theta equals 0 is trivially gapped. So that's a more precise conjecture. So when I said above that SUN Yang-Mills is gapped, you might, now that you've seen these possibilities, you might legitimately ask, could there be a topological field theory at long distances? And actually, the answer to that is sometimes yes. So in fact, while this conjecture is true for SUN Yang-Mills theory, if you change the gauge group at long distances, there generally is a topological field theory. So there is a kind of a rich story here, but we'll keep our focus simple on SUN. Okay, so that's the more sharp conjecture. Okay, so if you like this, this is the statement that SUN Yang-Mills at theta equals 0 at long distances becomes the most boring possible theory, the trivially gapped quantum field theory. Now you could ask, can this be true for all theta? And the answer emphatically will turn out to be no. And one of the main goals of this lecture will be to try and teach you the technique to rigorously prove this statement. So in fact, there's a result that I'll highlight. Result number 1. And this is due to Gaiotto, Komorgodsky, Kapustin, Seiberg primarily, and then it was also elaborated on a little bit by myself, Hotat Lam, and Nadi Seiberg. And what is result number 1? So result number 1 is that the infrared at theta equals pi cannot be trivially gapped. And I would like to emphasize that the conjecture up here about SUN at theta equals 0 is a conjecture. It is what we believe based on lattice simulations, other kinds of arguments, and it fits into a beautiful picture. But result number 1 is really a theorem. So there's really some new mathematical technique that you'll be able to use at theta equals pi to prove something. Okay, and like I said, by the end of these lectures, hopefully you'll be able to prove result number yourself. Okay, so in fact, even more can be said. What could possibly be even more? Well, let's look at the following facts. We'll look at that theta equals 0 and are special. So in general, we have these this circles work on field theories labeled by the theta angle, but theta equals 0 and theta equals pi are special. And why is that? Well, it's because there's time reversal.
Hi, Claire. There was a question in the chat. Sorry to
go for it.
Saying, is that the theta equals 0 case related to the Vafa-Witten theorem?
The Vafa-Witten theorem. Theta equals 0. Well, first of all, let me emphasize again that the status of, at least at the level of mathematics, of SUN Yang-Mills at theta equals 0 is a conjecture. It's a very well motivated conjecture that it's trivially gapped, but it's not proven. And any insight into that would be a real breakthrough in physics. There are techniques that work at theta equals 0 for controlling various symmetries. Those sometimes go under the name of Vafa-Witten theorems. But this conjecture is not really about that. Okay, so let's get back to time reversal symmetry. So what does time reversal symmetry do to the theory? So that t of theta is minus theta. So t changes the sign of theta. And the reason for that is that we have, why is that? Well, it's because f wedge f, if I unpack it, is like epsilon mu nu rho sigma, f mu nu, f rho sigma. And so if I act with time reversal, it changes the sign of the Levi-Civita symbol. And so effectively, we can think that that acts on the parameter theta by changing its sign. Okay, so these 2 points are special because they're fixed points under this action of t. So that means that theta, so for theta equals 0, that's obvious. 0 is equal to minus 0. For theta equals pi, that takes just a moment of thought. The reason theta equals pi is a fixed point is precisely because theta is periodic. So pi and minus pi are congruent modulo 2 pi. So what does that mean? It means that theta equals 0 and theta equals pi have t symmetry. Whereas general theta does not.
At the level of the action, like all theta are t, the theory is symmetric for all theta, right? Like that's.
What was the question? Excuse me?
At the level of the classical action, the theory is symmetric under t for all values of theta, right?
No. No, it is only symmetric for theta equals 0 and pi. This is an analysis of the classical action. So the classical action contains this term here, f wedge f, which is equal to this epsilon tensor contracted with f's. And if you act with t, it changes the sign of this term.
Right. Yes.
So in general, that does not preserve the action.
But when you impose t of theta is equal to minus theta, that preserves the sign, right?
That's right. Yeah.
Okay. Yeah.
So that's how you get, if you want t symmetry, you get zoomed in on theta equals 0 and theta equals pi. Okay. So if we're discussing the long distance physics of Yang-Mills theory, we should also ask what becomes of this time reversal symmetry. And let's in particular ask about the possibilities for theta equals pi. So we're particularly interested in theta equals pi because of result 1. So what are the different possibilities that are permitted according to result 1? Well, for theta equals pi, it could be gapless. This is possible, but it conflicts with our intuition at theta equals 0. So it conflicts with the lore at theta equals 0. So this, while it's mathematically possible, it would be highly exotic. So I don't mean to say that that is impossible, just that if you were really able to prove that Yang-Mills theory at theta equals pi was gapless, that would be very exciting. The next case, of course, is gapped, but because of the result that we discussed above, it cannot be trivially gapped. So this means a non-trivial TQFT. And then again, there would be subcases. So one possibility is that it's confined. By that, of course, I mean Wilson loops have an area law. So it may be a little bit funny to you to think that we're going to discuss confinement in the context of a topological field theory. But a topological field theory, one of the observables in it would be a Wilson loop. And so you could ask, what is the behavior of this Wilson loop in the topological field theory? And that would be a question that the infrared has to answer. So it could either be confined or deconfined. And then now that we know about time reversal symmetry, we can ask, is it T invariant? So I should put a question mark here. So this is the question of whether the vacuum preserves T. In other words, does it preserve T or spontaneously break it? So I can now tell you a second result, proved with very similar techniques. And this one is due to myself, myself and Kentaro Omori. And what is this result? So SUN Yang-Mills at theta equals pi cannot be simultaneously what? Gapped, confining, and T invariant. So that's an interesting constraint that one can prove. So I won't be able to prove this one to you in these lectures, but I want to highlight it so that you see that these new techniques are really very powerful. We are learning new things about pure Yang-Mills theory, a theory that has been around for decades. So something has to give. So even if you believe that the theory is gapped, it can't be confined and T invariant. And so what's the lore? If you like, what's the conventional wisdom? Although this is again a conjecture. The conjecture is that what gives is that T is spontaneously broken. So what does that imply? That implies that there are two degenerate vacua and exactly stable domain walls. So that's in a sense the state of knowledge about this problem.
There was one question on the chat, Clay. Was quite general, asking about what it says. What about Higgs phase?
What about Higgs phase? Well, right now we don't have any matter. We're just talking about the dynamics of pure Yang-Mills, and of course these techniques. So I'm giving you this as kind of a motivating general problem, and I'm giving it to you because so that you can see that hey, this abstract stuff which I'm going to talk about actually has really concrete implications for quantum field theories that you should care about. namely Yang-Mills theory. Now, of course, if you add matter, there's other things to do. There's lots of applications of these techniques, but there's no Higgs phase in this particular problem that I'm discussing. Any more questions? Okay, very good. So then we'll get started talking about sort of the next subsection. We're going to get into the techniques. And these are symmetry and anomalies. And so broadly speaking, what is our goal here? What we're going to do, and one way I like to think about this subject, is that we're going to develop a theory of renormalization group invariance. So concepts that are constant as you change the scale of the theory. And sometimes these quantities are referred to as 't Hooft anomalies. And the word anomaly is unfortunately extremely overloaded in physics, but to zoom in a little bit on the concept that one is interested in, we sometimes say 't Hooft anomalies. So I'll define what these are and explain some basic properties of them for the rest of this lecture. Okay, so what do I mean by an RG invariant? Oops, what happened to this? What do I mean by an RG invariant? So the first thing is that you actually, in a sense, already know a renormalization group invariant, which is that symmetry itself is RG invariant. So the concept of symmetry is itself the simplest notion of a renormalization group invariant. Let's unpack that a little bit. So imagine we have some UV theory, and it has global symmetry. Let's call it G. And what do we mean when we really say that? Well, what you should mean is that the local operators are in representations of the group G. So that's what we mean in a sense by saying that there is a global symmetry. We can organize our local operators into representations of G. Okay, so now we run the RG. Now what you will find is an IR theory, again with global symmetry G, and with local operators in representations of G. So this way of thinking about symmetry is always scale invariant. Now, there is a confusing point here. Many of you might be wondering, hey, what about spontaneous symmetry breaking? What's going on with that? So let me make a comment about that. So note, in the infrared, the Hilbert space in infinite volume, this might spontaneously break G. But the operators, the local operators, are always G invariant. So in a sense, when you first learned about quantum field theory, you're often interested in this Hilbert space on infinite spatial volume, like R3, the simplest space that you might study. And then you find that, hey, symmetry can sometimes be spontaneously broken. And that's a very rich phenomenon. But in a sense, it would be better to first introduce the fact that the local operators, no matter what happens to the Hilbert space, the local operators are always G invariant.
Excuse me, do you mean G invariant, or do you mean they transform under some
Sorry, I
representation
meant
of G?
representation are always in G reps. Yeah, I mean they're in representations. Other questions?
Could you not have something like emergent symmetries in the IR?
You could. That would mean that G is bigger, but G would still be there.
Ah, you're saying it can't shrink.
Yeah, it can't shrink.
Okay. Thanks.
More questions? Okay. Yeah, go.
But it's possible that G does not act faithfully in IR?
Yeah, so that's what I'm coming to now. That's an excellent question. So, so this is useful, but as was just pointed out, there's kind of a catch. Useful, but in the IR, G could act trivially. Or maybe a piece of G could act trivially, as was just suggested by this non-faithful comment. So, you know, just to get us on a concrete example so we all know what we're talking about, let's imagine we have a complex scalar. Let's call it phi with mass m greater than 0. So then in the UV, we have a U1 global symmetry, which is a phase rotation of phi, but the IR is trivially gapped. So we start with this U1 symmetry. And it's still true that in the infrared, the U1 symmetry acts on all the operators. It's just that all the operators, there's only the unit operator. It's in the trivial representation. So the statement above that I gave you about symmetry being RG invariant is holding here, but it's holding in a kind of boring, trivial way. So if you just focus on symmetry as an RG invariant, you might just get stuck with this kind of example. So what we'd like to know, so we'd like to ask the following question. So when can we be sure, when do we know that G must act in the IR? So how can we find the condition that ensures that the symmetry is still present in some guise in the infrared? And that's what we're going to get into now, finding such conditions. Okay, so what we're going to do is we're going to introduce source gauge fields. Okay, so we're going to probe the QFT, which has some global symmetry. Remember, we're trying to answer this question about making global symmetry act in the infrared. So we're going to probe the this QFT using gauge fields A coupling to currents J. So a little bit more concrete. Oops. Sorry about that, guys. A little bit more concretely, the action S we'll include in it now a new term, which looks as follows: integral d to the dx, a mu, j mu, where j mu was conserved. Now, there are several things before getting into kind of more interesting discussion about this. There are some important concepts to make very clear. So the first thing to make crystal clear is that A is a classical gauge field. What does the word classical mean? Here I'm using classical as opposed to, say, quantum. What I mean when I say that is that it is not integrated over in the path integral. So it is not dynamical. Instead, we're using it as a kind of convenient probe. So what that means is that if we integrate the dynamical fields, the ones that are actually fluctuating, this defines a partition function. I'll call it z, and z will be a function of a because a was not integrated over. What's the use of this z of a? Well, I'm sure that you've seen before that this encodes correlation functions. That is, by differentiating the partition function with respect to a and then turning off a at the end, we can read off these correlation functions. So that's the first use of the partition function. But as we're going to see, there's more sophisticated uses for it as well. So typically when you think about correlators, you're thinking about the xi as being distinct. So in correlation functions, J is conserved at separated points. That's what it means to say that J is a current for a global symmetry. But we could ask, what about contact terms? So what happens when the xi collide? Well, then J need not be conserved. And that's sort of the interesting part, interesting introduction to the concept of anomalies that we're going to get to now. Any questions?
Do we expect Z of A to be gauge invariant? Like, can we, like, is it invariant under the gauge transformations of A?
That's an excellent question. And that question is equivalent to this question about contact terms. So we can ask equivalently. Is Z of A plus D lambda equal on the nose to Z of A? So this is a question about gauge invariance for the background A. So these questions are equivalent because if we do a gauge transformation, we'll introduce divergence of J, right? The piece d lambda in that shift couples to divergence of J. So you can think that this is asking what's going on with the correlation functions of divergence of J. We know that there's 0 at separated points, but we don't yet know if there's 0 at coincident points. That's why these questions are equivalent.
I see. Okay, thanks.
Okay, so what's actually the general story? So in general, the answer is that it is not gauge invariant. What you'll find is that z of a plus d lambda equals z of a times an interesting correction term. We're going to discuss this correction term. So z is not exactly gauge invariant, but we're permitting a term here that is a phase correction. And let me say that this correction omega is local. So it's a local function.
There was a question, Clay.
Yeah, go for it.
Asking, is this related to ward identities?
Is it related to ward identity? Well, what we're really asking is yes. So when we discuss divergence of J, when I said it is 0 at separated points, the discussion about coincident points, one place where you know that divergence of J is not 0 is when it collides with the charged operator. So sometimes you have divergence of J hits a charged operator, and that gives you a contact term which is non-zero. And that's the ward identity. So what we're discussing now is corrections to the contact terms, or equivalently this question about gauge invariance, which is about contact terms that go beyond those due to charged operators. So it is related, but it's distinct. Okay, so this correction is local since J is conserved at separated points. By that I mean omega is roughly speaking some polynomial, and a and lambda and their derivatives. If it were not, if it were non-local, if there were multiple integrals there, it would be a violation of conservation at separated points, and that we don't want to permit. Okay. So we've encountered this funny phase controlled by omega. And what you do is you try to adjust our definition. So we try to remove it. You might say, this is just stupid, Clay. We'll try to, oops, I don't know how that happened. We'll try to adjust z of a by a phase to remove this omega. So we'll adjust z of a to restore gauge invariance. So what kind of adjustments are we free to do? Well, we can take z and we could redefine it as follows. So I can redefine my my partition function by tacking on this kind of extra phase. And if you think about what I'm doing here, I'm adjusting the contact terms. because this f I'm taking to be local. So this is something that we can generally do. We can modify our partition function in this way, and in this way we could try to remove that pesky phase omega. So now we come to an important definition. So definition. If omega cannot be removed by any f, we say there is an 't Hooft anomaly. So that's the term, 't Hooft anomaly. And the data of the 't Hooft anomaly is a kind of cohomology class. It's omega modulo the freedom to choose any f. So basic example, which everyone is familiar with, I hope. Basic example is the kind of anomalous triangle diagrams in 4D quantum field theory. You could imagine you have, let's say, Weyl fermions, psi alpha with charge qi. Let's give them an index I under a U1 symmetry. And we have three, we can look at the triangle diagram where we have three currents, J, J, J for that U1, and the fermions run in this loop. And everyone probably knows that this leads to an equation d mu J mu well, equals with a squiggle sum over I qi cubed times fa wedge fa. So this is an example. Well, what's the example? So this is a very similar to the, well, this is identical to the thing we were considering above. So in this case, we would have omega is something like sum over I qi cubed times lambda fa wedge fa. So that's a basic example. Okay, so the final thing that I want to tell you about.
Just maybe say something, because you have a 4 form on the right hand side, and maybe say what's happening with the form indices in that equation, just for the.
Sorry, what? You're asking. You're asking how to think of this as an this f wedge f. Here?
Yeah, no, because on the left hand side you're sort of using Lorentz labels, and on the right hand side you're using index free. Like this. Yeah, thanks.
Yeah. Any more questions, clarifications?
There was one on the chat asking, is the removal of omega related to Wilson loops?
Is it related to Wilson loops? I think the answer is no. Okay, so very good. So the final thing that I'd like to do about is that anomalies our renormalization group invariants. 't Hooft anomalies. So I won't rigorously prove this, but I'll give you kind of a sketch of an argument, so you see why this might be so. So let's consider Z of A and G, where now G is a background metric. So if we investigate, if we take G and we scale it up by some uniform factor e to the sigma, we probe long distances. Now we can use something called the Wess-Zumino consistency condition. The Wess-Zumino consistency condition is just something kind of elementary about commuting derivatives. So we can look at del sigma, del lambda, Z of A and G. So here, this del lambda means we do the gauge transformation, A gauge transformation. Sorry, let me put a log here. And this del sigma means I do this transformation up here. G goes to e to the sigma G. And the Wess-Zumino consistency condition just says that this is equal to del lambda del sigma of log Z. Okay, so what can we get out of this very basic equation? Well, what is the left-hand side? So the left-hand side, if I do del lambda of log Z, what I get is the anomaly, right? If I do del lambda log Z, I pick up that omega. And so if I do sigma variation of that, I'll get the scale variation of the anomaly. So that's how you can think of the left-hand side. Now it's equal to something else on the right-hand side. So if you, let's keep the del lambda outside. If you do del sigma of Z of AG, well, del sigma is this change in the metric. And it's just scaling the metric by an overall factor. So that's introducing the trace of the stress tensor. So that's like the integral of the expectation value of the trace of the stress tensor. And then we're supposed to ask about the gauge variation of it. Well, I claim that this should be 0. Why? This is because we expect that T is gauge invariant. Right? And that's what this is asking. This is asking, is T gauge invariant? And so if you think the answer is yes, then by this simple Wess-Zumino consistency kind of argument, you conclude that the scale variation of the anomaly is 0. Okay, so I have in the last negative couple minutes, I want to connect this and conclude by connecting this to the beginning of the discussion. Let's connect to the beginning. So Z of A is typically non-local. And as we discussed before, it encodes separated points correlators. Now, what happens if a theory is trivially gapped? If a theory is trivially gapped, all correlators of UV operators become contact terms. If they did not all become contact terms, then that would mean that the correlation functions of your theory had some interesting position dependence. And that's exactly what's excluded by saying the theory is trivially gapped. So what does this imply? This implies that in this case, if you have a trivially gapped theory, you can write the partition function in an extremely simple way. We can say that Z of A equals, it has to be local because all the correlators have become contact terms. So it has to be equal to some function, the exponential of some local function, f of A. So this is local. And this is, again, if trivially gapped. Sometimes, just to help you with the lingo, sometimes this is called, if you're a mathematician, you might call it an invertible field theory. And if you're a condensed matter physicist, you might call it an SPT. So these are just all different subfields names for the same concept. And now I would like you to note something extremely fundamental, which is that a trivially gapped theory has no anomaly. Why is that? Well, as we discussed before, anomalies are those omegas, those violations of gauge invariance that cannot be removed by f's. But on the other hand, in a trivially gapped theory, the whole partition function is given by such an f. So of course, it could be removed. So we note then that a trivially gapped theory has no anomaly. And in particular, if we turn it around, we get what's a lot of the juice for this subject, which is that a theory with non-zero anomaly cannot RG flow to a trivially gapped theory. So this is really the fundamental conclusion that I wanted to get to today. So we've learned that anomalies, 't Hooft anomalies, are scale invariant quantities. So we'll try to compute them in the UV. And then if we're lucky enough to find a non-zero answer, we immediately get a strong conclusion, which is that the long distance physics of that theory must be non-trivial in some sense. It cannot be trivially gapped. And that's what I meant before, and when I said that we were trying to find something to compute that would make the symmetry act non-trivially. 't Hooft anomalies are those things. Okay, I'll stop here for the day.
Thanks very much, Clay. Does anyone have any further questions?
I have a question. Most of what you discussed today pertain to continuous global symmetries. To what extent would the story change when you consider some discrete symmetries?
That's a good question. In a sense, the next lecture will be about sort of techniques for dealing with discrete symmetries. But the answer is not much. I've introduced the conclusions stay the same, even though some of the intermediate steps look different. So, I mean, if you go back up here, you might say that I did a lot with this current J, for instance. And we won't have a current if we're talking about a discrete symmetry. That's really the main difference. But in fact, upon closer inspection, you can determine that I didn't, although I wrote J many times, I didn't actually do very much with it. What I did a lot with is I did a lot with this background gauge field, this notion of coupling to a source. And so as soon as you can figure out how do you couple to a source for a discrete symmetry, if you can make sense of that notion, then the whole story carries through.
There's a question from Javier. Javier?
Sorry. Yeah, hi. You have shown that when you do this gauge transformation, the partition function can be modified by this exponential term. And but then, so if we have seen that the partition function can change under the gauge transformation, what is the argument that the expectation value of the stress tensor is bound to not change under such gauge transformation?
Yeah, that's a good question. So so indeed, this is a little bit of a slick argument, and it has some when I introduced it, I think I said that I was going to kind of motivate the conclusion, not really rigorously prove it. So one reason why you might expect that T doesn't change under gauge transformation is because one hallmark of the stress tensor is that it's neutral under all global symmetries. So that should make you think that T is decoupled from this notion of from these gauge transformations, but it's not really a rigorous argument. And in fact, to really prove this statement requires a kind of different bit of technology that I didn't really want to get into, but I'm happy to discuss in more detail later.
Okay, there's a few more questions.
Just wanted to comment that I agree that the T mu, that the stress tensor is itself invariant, but what I'm worried about is that you are taking the expectation value in a background that is not gauge invariant.
No, well, okay. I'm taking it just in a background A. I completely agree with you. There is something else to say there, and in order to really give a rigorous proof of this, I would have to introduce some topics of anomaly inflow and things like that, which are a little bit too technical for the first lecture. So I sort of deliberately avoided them.
Thank you.
Okay, there's a few more questions on the chat, Clay. So one is, how can a topological theory be confining?
Okay, that's a good question. So, well, in a sense, we'll discuss this next time, I think. So the key question is to say, what does confining mean? Where did I, that was up here. Right, so the question is, what does it mean for a topological field theory to be confined or deconfined? And well, what we'll see is that is that in fact that's a very natural notion in a topological field theory, and it's a statement about the behavior of certain Wilson loop observables in the topological field theory. So I will define that next time. This is how we're going to get into the notion of generalized global symmetry. You see, maybe just to elaborate a little bit on the motivation, part of the trouble, part of the confusion for me before getting into this subject is that these two notions here that we're talking about, namely confined and T-invariant, they seem to be sort of fundamentally different. T-invariant is easy to understand. We're supposed to ask if the vacuum preserves a symmetry. And we understand what that symmetry is. We understand how it acts on local operators, et cetera, et cetera. But what about confined? When you first read about what confining means, you have to jump through all these sort of hoops where you say something about asymptotics of gauge transformations, or maybe you say something about area laws and perimeter laws. And it would be really nice if there were a symmetry-based formulation of confined and deconfined. And that's actually what we're going to introduce next time. We're going to learn how to think about confinement and deconfinement from the point of view of symmetry, so that it will be just on the same footing as T invariance.
There's another question. If one cancels anomalies in the UV with, for example, the Green-Schwarz mechanism, then will the IR theory be trivially gapped?
If one cancels anomalies with the Green-Schwarz mechanism. So, I mean, let me turn this into a good question. So the Green-Schwarz, I mean, the Green-Schwarz mechanism in quantum field theory or string theory is really just saying that tensor fields contribute in interesting ways to anomalies. So you know, that discussion about the Green-Schwarz mechanism is really sort of separate from this. But maybe the second part of your question is about what happens when the anomaly is 0. So we could have imagined that the anomaly is 0. And that's often the case. Often quantum field theories have trivial or 0 anomalies. And you can ask, what can I conclude about the infrared of a quantum field theory with 0 T-drift anomaly? And the answer is not much. I can conclude only that it's consistent for it to be in any of these classes, any of these broad classes. So, so I don't get much when I have 0 anomaly.
Okay, so we're actually running out of time in the sense that we have a tutorial coming up in 2 minutes. I want to remind the participants that if they want to ask more questions, or if your question, because I noticed a couple of questions came in just now, you can ask them on the Slack room, or whatever the right terminology for that is. There's a Slack channel. Slack channel, I think, is the right terminology.